In this video, which is lesson 2 from the second part of Unit 5 in Calculus 1, we're going to be talking a little bit more about definite integrals and the notion of positive and negative areas and accumulated change. In example 1, we're talking about the function 1 minus x squared, which is an upside down parabola that's been shifted up 1 unit on the y-axis. Here is a calculator display of that function. We would like to evaluate the integral in part A using a midpoint Riemann sum between x values of 1 and 3 with the number of subintervals being 4. So if you don't have a graph to look at, sometimes it's helpful to consider, say, a number line. If we're going to look at the distance between 1 and 3, and I would like 4 subintervals, well, I could cut that in half, and I've got now 2 in the middle, and then half again, and now I've got 1.5 and 2.5, and this is what's going to allow our 4 subintervals. Those are the edges of the subintervals. Now, because part A is a midpoint Riemann sum, well, I need to take the height of the function at the middle in between these two boundaries and use them to adjust or define the height of the rectangles. So now I'm talking about an x value of 1.25, 1.75, 2.25, and 2.75. So mentally, if you're aware of that, then I think computing the Riemann sum is going to be a little bit more straightforward. So the midpoint sum would then be equal to our delta x times the y value of the 1/2 mark plus y value of 3/2, all the way up to the last position minus 1/2. Now that's just kind of a formal way to describe it. I'll leave that up to you whether you want to show this setup or not. But essentially what it comes down to for us is the width of each rectangle, in these cases, is half of a unit. And the height of each rectangle is based on these x values. So the first height would be 1 minus 1.25 squared. The second height, the third, and the fourth would follow much the same way. Now, this series of multiplications indicates the width of each rectangle times the 4 different heights for our 4 subintervals. Certainly, we would use a calculator in this case. I wouldn't expect you to do this by hand or in your head. But what's interesting is that the result comes out to be negative 6.625. Now, how do we get an area that's negative 6.625? How do we obtain a negative area? Well, here again, in this particular example, we're looking at x values between 1 and 3, and we did end up with 4 subintervals whose heights were determined by the midpoints of those intervals. So if I'm looking at those rectangles, they're going to look something like this. Here's our first rectangle, the second, the third, and the fourth. So much like before, we're going to have an overestimate and an underestimate built into each of these midpoint sums. We're technically below the graph here, but we're above the graph here. So these sections still represent our over and underestimates, but that doesn't quite explain why we're getting a negative result. Now, if you're assuming that we're getting a negative result because we're below the x-axis, you're absolutely correct. And so that's important to recognize that when we compute area that falls below the x-axis, that area is going to be counted as a negative area. And in terms of geometry, that doesn't make a whole lot of sense. How could we have negative area? But if we talk about accumulated change based on derivatives. For example, if our y-axis represented our velocity in miles per hour and our y-axis represented velocity in miles per hour and our x-axis represented hours, we should recognize that the units, when multiplied, miles per hour times hours, generate the unit miles. And when we talk about area here we had positive velocity, but it's decreasing. And then eventually we encountered negative velocity. So negative velocity implies that we're changing direction. And if we had positive velocity for some of the time, that means we were moving in one direction. And then negative velocity the rest of the time, well, then we moved in the opposite direction. And as it turns out, we moved in that opposite direction more than we moved in the original direction. So therefore, the accumulated change, or total distance traveled in this particular case, ends up being leftward, or the opposite direction from which we began. So it is a negative area in a sense, but it makes more sense and it's more reasonable to consider this as a negative amount of accumulated change. Now back to this example, if we complete a left-hand Riemann sum between 0 and 3 with 6 subintervals, well, again, let's think about the distance that we have to cover here. We have to go from 0 to 3 in 6 subintervals. So I could try cutting 3 in half and then in thirds, but it's just as easy to chop this by 6. 3 divided by 6 is 1/2, then 1, then 1.5, 2, and 2.5, and 3. So these subintervals, I think, would be sufficient for 1, 2, 3, 4, 5, 6 rectangles. And the heights of each rectangle are determined by the left-hand sums, so from 0 up to 2.5. For our left-hand sum, the delta x times the y values from y0 up to, in this case, y5, the 5th data point, not the 6th one. We're excluding the 6th one because that's the right-hand side of our interval. And our delta x, the width of each of these rectangles, is 0.5. And our y values can be calculated the same as before. Now, one thing to make it interesting and to kind of bring in the discussion from last video is that I can use this delta x, this 0.5, times the sum of an expression, and we're using interval values from 0 up to 5, remember? So 0, 1, 2, 3, 4, 5. Those are the positions. From 0 to 5 of the equation, 1 minus, now I've got to be a little bit careful here, n divided by 2 squared. And I have to use divided by 2 here because I'm trying to recreate these specific values using that summation notation. So when n is 0, 1 minus 0 divided by 2 squared is 1. So the height of that function is 1 on the left-hand side. When I use an n value of 1, 1 divided by 2 is 1/2. So 1 minus 1/2 squared gives me the height here, and so on. And I'm essentially creating the left-handed boundaries for these rectangles. So again, n divided by 2 was just the technique used to establish each of these x values that were then squared inside of the function. And certainly I would expect you to be able to repeat this on paper with a simple calculator if you needed to. Even if you didn't use the summation notation, you should be able to account for this. 0.5 times the heights of each of these rectangles. Now I didn't list them all, but of course you could do that. But also I wanted to point out something to you as well. If you are using a TI calculator, I think this is available on both the CAS and the non-CAS version. If I'm misspeaking about the non-CAS version, then somebody can correct me here. But if we create a new document, and add a calculator page. Inside the menu option within our calculus subgroup, there is an option to execute a series of sums. And so we can call upon that sum command and specify that we want, say in this case, from an n value of 0 to 5 of the expression 1 minus, we said n divided by 2 quantity squared. I guess I didn't need that double set of parentheses. And all of that's multiplied by our delta x, which is 0.5. And then when we press enter, we do see the calculated result, and we get negative 3.875. So even if I performed all of the math laid out this way, I would still end up with the result, negative 3.875. Now you may be wondering, why is this area different than the last one? Well, remember we made two changes here. Number one, we had more subintervals, so we should be more precise with our answer with more subintervals. We're closer to the correct result. But also, and perhaps more importantly, our interval itself actually changed, not from 1 to 3 anymore, but from 0 to 3. And so when we talk about the areas associated with these rectangles, there are some rectangles whose area is above the x-axis, and there are some rectangles whose area is below. Clearly there's more area below the x-axis, so therefore our net result ended up being negative. Now speaking of net area, just one quick comment that I want to make about that is that sometimes we will use integral calculus to compute geometric areas, actual areas. And the problem with calculus is that area above the x-axis, of course, will be counted as positive, but area below the x-axis will be counted as negative. And when we sum those two areas together, we get a net result. In the event that we're interested in the total area for the actual shape, so if we were actually trying to describe the area captured by this particular curve, including the area above and below the x-axis, if I wanted to know that real area, a lot of times what we'll end up doing is we'll subdivide the integrals. We'll calculate the integrals where the results are positive, calculate the integrals where the results are negative, and then essentially account for this negative area by subtracting it. When you subtract the negative area, the net result becomes positive. And so that's what the instructions up here are kind of reminding us, is that we can apply that trick if there's a need to calculate physical area as opposed to accumulated change. One example off the top of my head of where that might be important is maybe we're looking at a top-down view of a satellite image, and we're trying to estimate the area associated with a lake. So the lake might have an irregular shape, and we need to compute the area of that lake. Well, what we could do is with some regression analysis, we can find the equation that represents the shoreline of this lake. So again, we're looking top down here, and we can create a function, and we would likely do this in two parts. We would create a function or some sort of equation that describes this lake edge, and we can integrate that area using our definite integral process that we were just describing, and that would account for the area associated with that portion of the lake. Now down here, this is not technically a function anymore, but we can do some sort of equation analysis to find the equation that represents this shape, and we could use a form of implicit differentiation or integration in this case to accumulate the area. But if we were to calculate the area based on this orientation, this area would be counted as negative because it's below our x-axis. Well, clearly we want the total area, not just the area above the x-axis, but the area below the x-axis to be counted as whole as well. And so we would use this trick to correctly identify the total area associated with this particular shape, even though some of it lies above and some of it lies below the x-axis. This diagram was left over from the last problem's discussion. Here you can see the specific area above the above the x-axis, and the specific area below the x-axis, and the sum of these two is what generated the negative 3.875. Now, just to connect the dots further from last week's discussion, here's the formal definition of what we call a definite integral. And a definite integral is an integral using the same notation that we were describing last week, this scripted S. But now we have boundaries of integration, lower boundary and an upper boundary. The textbook tends to call these lower limits and upper limits. You'll hear me say the word boundary because I don't want the word limit in this case to be confused with the actual calculus description of limits. But as we were saying last week, this definite integral evaluated at a particular function with respect to variable x is essentially the same as the sum of all of the areas of the rectangles. Now here's the width of the rectangles. The function calculated results are the heights of each rectangle. So if I add together the widths and, the heights times the widths and added together all of those, as we made our delta, the change or the width gets smaller as it approaches 0, or as the number of subintervals as they increase towards infinity. It's this combination of the limit notion with an infinite number of sums of areas that allow us to calculate this definite integral. Now, fortunately for us, this definition is not a significant component of this particular class. I think as long as you're aware of the process where we can reduce the widths and increase the number of rectangles in this case to get a better approximation, I think that's pretty good to understand. And obviously 6 intervals is not nearly as accurate as 40 or 75 or an infinite number of intervals with infinitely narrow width. But ultimately, as it turns out, as we evaluate these sums of areas using limits, we do obtain the specific definite integral. Now again, with this definite integral notation, we'll just kind of ignore this for the time being. You'll again hear me say upper boundary and lower boundary instead of limits. Either one I think is acceptable. So upper boundary and lower boundary of integration, that's what these numbers or values are going to be called. And then the function on the inside has a special name. It's called the integrand. And you'll also hear me say that x, in this case, is our variable of integration. And you'll also sometimes hear me call this the differential. So those are just some vocabulary terms that you're going to be hearing throughout this unit. I'm sure you've heard some of them already. But just in case you're reading on your own or listening to other instructors on YouTube or other websites or other classes, hopefully you'll recognize these phrases and understand what they mean in terms of the problems themselves. So to finish out this video, I'd like to complete just a couple examples. Now I think we'll evaluate these definite integrals. They look like calculus problems, but we'll use geometry to address them right now. And at another time, we'll practice the calculus concepts. In fact, we've actually started some of the calculus concepts in our classroom discussions, but for right now, let's use geometry. So in part A, we're being asked to find the definite integral between a lower boundary of 2 and an upper boundary of 4 of this particular function. Now, our variable of integration here is x, so I'm going to go ahead and label the x-axis and the f of x-axis, or our y-axis. And the graph 2x plus 3 is a linear function with a y-intercept of 3 and a slope of 2. Now, if I draw a slope of 2 where each grid line is 1 unit, that's not going to fit in this space very well. So I think this scale would work just fine. It's 2 units per grid line on the functions axis, and then it's 2 grid lines per unit on the x-axis. I think that would be good. So now when I identify the y-intercept of 3, that's here, and to have a rise of 2, we would rise up 2 units, which is 1 grid line, and over 1 unit, which is 2 grid lines, and that would be here. So this is going to be the shape of this particular graph. And it does continue indefinitely. So we'll go ahead and connect those with a line. Now we're being provided boundaries of integration this time from 2 to 4. We're not just finding the antiderivative, but we're finding the integral, the definite integral between 2 and 4. So this lower boundary of integration, or lower limit of integration, is here at 2, and the upper boundary, upper limit, is here at 4. And we're essentially being asked to find the area underneath that curve. And even though this is a straight line, we still call this a curve. Now, using geometric concepts, we should recognize that this shape is a trapezoid whose base number 1 is equal to 11, or you can call this base 2, it doesn't matter. But the height here is 11, and the other base is equal to 7. And so the height, which is a little bit misleading because it's sideways here, the height is equal to 2 units. And we have an area formula for trapezoids that is equal to the average of the bases, so base 1 plus base 2 divided by 2, multiplied by the height of the trapezoid. So we've got 11 plus 7 divided by 2 times 2, and our area computes out to be 19 square units. Sorry, 18 square units. We can check our work if we have a CAS calculator. Again, I think the summation is available in non-CAS calculators, but I may be wrong there. I do know that this integration, strike that, I almost said something incorrectly. I just went and double-checked with one of our handhelds in the classroom. The sum function does exist in our calculus menu. It's option number 3 on the non-CAS calculators. But we do have an integral option. It says numerical integral on our non-CAS calculators. But as far as I can tell, it does operate the same way as the instructions on the CAS calculator. So let's see what we get. The lower boundary was 2, the upper boundary was 4, and the function that we are integrating was 2x plus 3 with respect to the variable x. And when we press enter, sure enough, the definite integral does come out to be 18. And we established that using geometric methods just a moment ago. So that's nice to see. And that'll make me rethink the calc permitted and not permitted portions of the test, but I'll worry about that. You don't have to. In example B, I think a y-axis where 2 units per grid line would be appropriate. So if we had a graph with a y-intercept of -6 and a slope of 2. Now a slope of 2, when we rise 2, that's 1 grid line, and when we run 1, that's only 1 grid line. So it may be a bit misleading, but this particular graph with the modified scale does indeed have a slope of 2. So we're talking about this particular function, and we are integrating on the boundary from 1 to 6, which is just off the edge of the graph here. So think about what's going to happen. We've got area beneath the x-axis, and we have area above the x-axis, both of which are triangular in shape. So go ahead and pause the video now and compute the net area. Since this question is asking for the integral, we will count the area below the x-axis as negative and the area above the x-axis as positive. There would be further instructions telling you to calculate the actual area as opposed to integral results. So again, pause the video now and resume playback in a moment to check your work. So in this case, we had to be extra careful because the height of the rectangle, based on the new scale, may have been a bit misleading. But the area, 1/2 base times height, the base in this particular case was 2 units wide. The height was 4 units tall. In this example, the width, or the base, was 3 units wide, and the height was 6 units tall. So the area for each, respectively, was 4 and 9. So the result of the integral would be the positive area above the x-axis minus the area below the x-axis, and we should end up with an integrated result of 5. We can check with the calculator. Again, menu, calculus, integral. The numbers may be different on yours, but the process is going to be the same. And we'll evaluate between 1 and 6 on the function 2x minus 6 with respect to x. And here we go. The integral result is 5, just as we expected. Now this last example is kind of interesting. If you recall, we can graph a semicircle with the expression r squared minus x squared underneath a radical, or I think more traditionally, well, no, I think this is the most common method, r squared minus x squared, because this is a derivation of our equation of a circle where r squared is equal to x squared plus y squared. By the time we isolate the y variable, it tends to be r squared minus x squared, and then we'll square root both sides. So anyway, this is a generic form of a semicircle, and if I were to apply transformations to it, say a positive 1 inside of the grouping symbol and then a minus 3, and by grouping symbol I mean the square root sign. Actually, let me take that back. That's going to act as our radius. So if I apply a minus 3 on the interior of the grouping symbol here, that's going to shift our graph to the right 3 units. So now we have the center of our semicircle right here, 3 units to the right, and the radius of the semicircle, of course, is 1, because 1 squared is 1. So we're now dealing with a semicircle that looks like this, and the boundaries of integration are indicated as 3 to 4, and so we would like to find the area under that curve. Now, using calculus by hand would be fairly difficult in this particular case. And we'd either have to use some sort of substitution methods or integration by parts, which we haven't even gotten close to discussing just yet. But as far as geometry goes, we can compute this area pretty directly, because the area ends up being 1/4 of a full circle. If we had the full circle here, this section is literally just 1/4 of that. So pi times radius squared, and in this case we have a radius of 1, so 1/4 pi times 1 squared, and as it turns out our area should be just pi over 4. And if we reach for our TI calculators to confirm, we can jump into the calculus menu and select integral. Our boundary of integration will be from 3 to 4. The expression 1 minus the quantity of x minus 3 squared, and the integral is evaluated with respect to x. And when we generate the result, this CAS calculator does give us the precise answer, pi over 4. On a non-CAS model, we'll probably get a decimal, 0.78539, and that is 1/4 of pi as well. So I hope this discussion in this video helps clarify some things. As we move forward this week, you're going to have an opportunity to practice computing definite integrals by hand, and then of course checking your work with a calculator. I would prefer you not to use the calculator to find the solutions, rather instead compute them by hand using our new methods first, and use the calculators to just check your work. If you have further questions, please let me know. Otherwise, thanks for watching.